Does buddy reading go for the whole lesson?
Yes, buddy reading goes for the whole lesson.
Wait,
And we're recording this.
So we shouldn't bitch about it.
We'll do that afterwards. Okay, so this is like my favourite topic because one, it's really cool, and two, it's really short. So we have thus far looked at. We've been like, light's a wave. No, it's not. It's a particle. And now we're going to be like, no, particles are waves. All right, just to mess with your heads a little bit. So we're going to, go through those things. It shouldn't take us very long. Okay, so consider this. Why is it doing that?
The pen's not counted as these.
That didn't work.
No, it's just playing up. There we go. Good. Okay, so we can't see light. We can see light, but we can't see what it's made up of. Right? So we just make guesses, we make inferences about it, about its nature. So it could be like little lemmings and they carry the little light and they have little torches and they could turn it on. It could be that. It's probably not that, but it could be that. But we wouldn't know, gals. Shh. Only because I'm recording, otherwise I probably wouldn't mind that much. So we've seen that it behaves like a wave and also that it acts like a particle, but we can't see it. For the same thing, we can't see subatomic particles. We don't know what electrons look like. We don't know what protons or neutrons look like. We don't know what the atom looks like, really. It could be like purple and with a a sailor's hat on or something like that. It's probably not. So we basically, from classical physics, we only assume that they act like particles. We don't know that they're particles. Same idea as light there. So, what if they didn't act like particles? What if matter, like this desk, or this whiteboard, or Drew, didn't act like a particle but acted like a wave? Then that'd be confusing. So this is what de Broglie. So Louis de Broglie, he was a student in 1923 and he's working on his PhD, which is his doctorate. And he's quite foolishly, but it worked out well for him in the end. His statement for his doctoral degree was that particles exhibit both wave and particle behavior. And basically he suggested that there's this wave-particle nature of electromagnetic radiation and it's common throughout everything else. So basically he suggested that there was a symmetry between light and matter. And guess what? The topic that we're covering, the major topic, is called light and matter. So de Broglie started by finding a way to assign a wavelength to a particle. Okay, so same as last week, we were like, oh, you can't give light momentum. Oh wait, yes you can if you do it this way. Because we originally said momentum needs mass, then we're like, hang on, it can have relativistic mass, so then that's fine. He also came and worked out, using Crompton's work from before, that the momentum of a particle is equal to h over lambda. So Crompton did that and had proven that before de Broglie came along with this idea. So we saw that last week. Very briefly last week, but we saw it last week. Which allowed for the calculation of momentum of photons. He suggested that this could be used for particles. and he ended up with this. So the wavelength of any particle is equal to h, which is a constant, that's Planck's constant, over m times v. So I am standing relatively still, and by that I mean relative to the Earth. I am standing still. What is my momentum? 0. If my momentum is 0, what is my wavelength? 0.
9.
Well, actually it's undefined because 0, a value divided by 0 doesn't work.
Yeah.
But, you know, it's not anything. It's an undefined. So, it's only when you're moving that you have one of these. So this is known as the de Broglie wavelength of a particle. So, fun fact about de Broglie then. So he did this in his PhD, and he got the Nobel Prize for his PhD, which doesn't happen very often. It's like 2 or 3 people that have done it. So this guy was pretty young, and he was like, oh, I'm going to do this really difficult thing, and was 100% correct, and got a Nobel Prize for it. So, yeah, very smart. And then he spent time hanging out with Bohr and Einstein and Schrodinger and all those other really famous physicists.
The balls.
Yeah.
Together.
Very briefly, very fun fact about Niels Bohr. He won the Nobel Prize, which is awesome. And his native country, Poland, was so proud of him that everyone was like, giving himself. One of the beers that's from Poland is Carlsberg.
They tapped into his house.
And they built him a house and then piped beer to his house. So he had a beer tap for the rest of his life, directly from the factory. So not having to sort out kegs or anything, he actually just had, it was like turning on a water tap. He turned on his beer tap and it just came from the factory.
That's
Which is pretty. I think the house was near the factory, but it's still that's pretty cool.
So it's just like radioactive and Nobel Peace Prize.
Yeah, well, no, the Nobel Peace Prize is rubbish, but
Yeah,
the Nobel Prize for Physics, I could get that one.
Yeah, the beer from the factory.
Knowing my luck, I'd do something that's maths and not physics, and there's no Nobel Prize for math.
Yeah, that's true.
There is a Fields Medal, though, so that's pretty cool. So we can calculate the momentum of a particle from its energy to save time. So instead of working out the momentum beforehand and having to know the speed, which we may or may not know, we can work it out like this. So just a little bit of rearranging. So that is there is your Ke equals what, half mv squared, which we all know. We've been seeing for the last year and a bit. Then we can rearrange that. We have 2 times E, so double the kinetic energy equals mv squared. Then we can add an m to this side and add an m to that side. If we do that, if we put one thing on one side of the equation and one thing on the other side of the equation, has it changed the nature of the equation? No, it hasn't. It's just put an extra thing to work around with. They're both squared. That can be written as p squared equals 2me. Therefore, momentum of any system is square root of 2 times the mass times the energy. And by that, any system, I mean any system with mass. So if I told you the energy, say it was an electron fired through a potential difference of blah, I told you the energy there, I told you the mass, you know 2. I think you should be fairly well acquainted with 2 by this point. You know how to do a square root. You can work out the momentum without having to do any rearranging, mucking around using this equation, which can be a pain.
Oh, really good because I drank warm beer over there.
Well, yeah, but room temperature, it's pretty cold in Europe. Yeah. Yeah, but as I just said, it's very warm over there very cold over there a lot of the time.
Don't keep them in fridges, keep it-
That's not the case for everyone.
Just open the cupboard, go with the beer out.
Yeah. So to be able to say that we have observed, Wiley, can you put your laptop away? Thank you. To be able to say that we've observed the wave behavior of particles, we'd have to be able to say that we can see interference and diffraction. So that might be an issue for this theory, wouldn't it? Because those things might be very difficult to see for particles. You don't expect Connor to run through the door and split up, do you?
No.
You also don't expect him to interfere with himself and cancel himself out. Neither of those things you expect to see. But, and to do this, the biggest problem is we would require gaps so incredibly small that we can't produce them. But I tell you what can produce them. It's crystals.
I can make it.
Make it very small, yeah, make it very small. You can get a quartz crystal, and the gaps between that are very, 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 very close together. Through that, we have observed that matter sort of behaves a bit like X-rays. It's pretty cool. So, not long after de Broglie was doing his work, in fact 4 years after de Broglie did his work, Clinton Davidson and Lester Germer, known famously as the Davidson-Germer experiment,
What was it called that?
no idea, for investigating the scattering of low energy electrons off a nickel target. So we've got really low energy electrons, and by really low energy of electrons, we mean like pretty energetic, but small and electronic. And they've got a nickel target, and they're bouncing them off the nickel target to see what happens. In a mistake, which turned out to be a really, really, really useful mistake. So sometimes accidents happen, and sometimes accidents are good for physics. The vacuum sealed on the experiment was broken. Oh no, you think that's going to ruin their results. And the nickel became oxidized because nickel does oxidize readily. In fact, what do we put nickel on? The roof? So, chemists, what do we call that? Well, yes, oxidization, well done. You're not a chemist though, so we do it as a sacrificial thing. So the nickel oxidizes, not the steel or whatever our roof happens to be made out of, the iron. So it became very badly oxidized. They heated up the nickel to remove the oxidization, which is something you can do. And started up the experiment again. To their surprise, they found that the beam of electrons were reflecting with intense maxima and minima. So they were getting points where they were getting lots of electron and no electron. Lots of electrons and no electrons. What does that remind you of? Interference of light. Interference of lasers, interference of light. When it goes through a small gap. So we've got an even smaller gap here because of the crystalline structure of what they've got there. And this causes the electrons to interfere with each other. This is very similar to X-rays. We're talking about the same amount of energy here. Basically, that's because of the way that that X-rays are produced. Which we'll get to later in these lectures. Heating up the nickel caused the nickel to align the crystalline structures, so you have these gaps. You have, nickel, as my two fingers there, gap, more nickel, gaps like that. Sort of like a diffraction grating. And this was the first direct proof of de Broglie's hypothesis, so that's pretty cool. So it only took 4 years to prove what was a pretty massive claim.
But if that mistake didn't happen,
I think eventually it might have. But yeah, you're right. Sometimes these accidents jump science forward 50 years, you know. So it's pretty cool. The following data was obtained by Davison and Germer. They found that the energy of their electrons was 45 electron volts. That is not 45, it's 54. 54 electron volts. They found that the first reinforcement maximum was at 50 degrees. That the interatomic spacing between nickel atoms was this, 1.215 nanometers. That is a lot smaller than our diffraction gratings we have here in the lab, which is roughly that. So they've got that data. That's the data it's very small. It's like that small. They've got that data. And they're like, cool. And then they put it into some equations that we know. This K equals 1/2 mv squared 1. They've just rearranged it. And they've worked out a speed. And the speed is 4.36 times 10 to the 6 meters per second. Is that an allowable speed? Can we do that speed? Is it less than the speed of light? Yeah, it's less than the speed of light. So that's fine. That's good. It's very quick, but that's good. And then they took that and they put it into this P equals mv, and they've worked out that the momentum is this really tiny value. And then they've worked out that the Broglie wavelength of the electrons. So all of this using stuff that we sort of already knew, plus this bit here, which we learnt last week. Now, think about that wavelength for a sec, okay? And we're going to go over the page, and we're going to use our d sine theta equals m lambda, and we're going to do that for a we're going to keep doing it for this, but this would match up with an X-ray. Okay, so we're going to put in, we knew the gap between the crystals, we knew the angle, we knew what was the first order maxima, so m equals 1. So the only thing we don't know there is the wavelength. So we substitute in all our values, and we end up with this. Is that value there, and the one from the previous page,
very similar.
very, very similar? Yes, within what we would consider to be like a small margin of error. So they match up. Hey, that's awesome. And yeah, as I said, this is evidence of de Broglie's hypothesis. So de Broglie was chuffed. He was really happy. Most people who win the Nobel Prize are very happy because it comes with $1 million prize money. Each Nobel Prize. Okay? Okay, I knew that question was coming. I'll digress very quickly. Okay, so Nobel Prize comes from Alfred Nobel, who discovered, do we know? Dynamite, TNT. And he was so pumped about this thing, he thought, with a weapon this destructive, no one could ever possibly think of going to war with someone else again. And he was so incredibly wrong, but he did live long enough to see that what he thought would stop people from fighting turned into a weapon and used. And then he sort of died. He didn't.
Yeah,
They reported him dead, and the newspaper slammed him, just said this is the worst example of a human being. He's invented this weapon that kills people, hundreds and thousands of people. He never gave away a cent. Basically, you've seen The Christmas Carol? or you know the story of the Christmas Carol, where the three ghosts come to
Yeah.
visit him in the night. Basically that, except real. And he was like, well, I have to do something. And he set up the Nobel Prize. All of the money that goes to the Nobel Prizes today still comes from his original money. And that's like 150 years ago. He was so fabulously rich.
And it would have been great
Yeah, and it's increased. And there's a trust that invests some of that money to make more money. It's very complicated thing. But yeah, that's where it comes from. So that's where the money for the Nobel Prize comes from. Let's get back. What happens when they run out of money? I think Sweden will probably prop it up because it's a big thing for them. Because he was Swiss. I think he was Swiss. One of those countries. One of those Europe countries. Not Russian. Definitely not Russian. Yeah. No, I'm just not sure. It was either Sweden or Switzerland or Norway or like, for all I know, Italy. One of those European countries. Connor's looking it up. Cool. Let us do this while Connor looks it up. Okay. So, electron microscopes. Guess what? We're into the application already. Stockholm in Sweden. Thank you, Connor. I was right. I did say Swiss, didn't I? Sweden? Swede. I got them wrong. Sweden is Scandinavian, though. Yeah.
Isn't it Russian?
It's probably part of Russia. Okay. At one point. Okay, so electron microscopes. We're into the application already for this topic, which is awesome, which means we are almost done. So, electron microscopes are like optical microscopes, but they use electrons instead of light. What is the advantage of that? What's the advantage of using an electron? If you, say, have a magnet and an electric field, it's got a charge and it's moving, so you can do what with it? Well, you can produce a magnetic field, but what can you do with your magnetic field? So I've got a beam of electrons going towards Connor, and I've got a magnet here. What can I do? I can deflect it, or I can make sure it definitely hits Connor. Just sort of aim it a little bit higher so it's going straight through their brain. So instead of using lenses to focus the light, it uses magnets and electric fields to focus the light. That is really awesome, really useful because, yeah, once light gets to a certain wavelength, it becomes indetectable for us. What is another advantage of electrons? When it hits a sensor, it can set off, it can be a very small, just electromagnetic sensor, and it can set it off. It's cool. So we've got, this is a basic optical microscope, and who invented that? Not you. Damn, I didn't think I did, but I thought I'd give it a go.
Was it James microscope?
No, it was not James microscope. It was not Alfred Nobel.
Alfred microscope.
Okay, if you guess in physics, if you guess one man's name, you are 50% chance of being right, and it is not Einstein. Not optic. Newton, it was Newton. Yeah. Newton. There were microscopes and telescopes before this, but they weren't very good. He invented this one. With different sized lenses and all this complicated stuff. Okay, so light comes through here. Light comes through here past the object, and because of a complicated array of optics, it produces a larger image. And the image would appear there. Images in microscopes appear upside down. You know this? You looked under a microscope before and you've tried to move the stage that way, but it's gone that way. Yeah, it's sort of annoying. There are limits to optical microscopes. The ability to distinguish between two objects that are closer together than the order of the wavelength of the radiation that is used is one of the big ones. So if you have light waves coming in, say red light, the gap between the two objects you're trying to distinguish can't be the wavelength of red light. Otherwise you just get a blurry mess. That's one problem. We can use higher frequencies, but what happens if you keep using higher frequencies, particularly if you're light, you've got an optical bit and you're looking into it like this? What happens to your eye? Well, it would probably blind you, yes, but it would also, you would not be able to see it because it's a high frequency, and what high frequency can we not see? Not high frequency, the other way. Ultraviolet, X-ray, gamma ray, cosmic rays. We can't see any of them. So, yeah, Connor did once. Basically, and X-rays. I think I've said X-rays in there. Did I say X-rays? Yeah. So we can't do that. We couldn't use X-rays anyway because they're really hard to focus. In fact, they can't be focused with lens. Basically to do with the size of the X-ray and the size of the lens and all this complicated optics stuff that we don't go into. So, we have a limit, an absolute limit that optical telescopes can work at. We had to invent these or not see small things. Smaller things. Electrons can be used to create images of small objects because their wavelength is very small. Their advantage is that they are moving charged particles. Hello. Yeah, so their advantage to the moving charged particles, and they are moving, so they've got electric field and a magnetic field. And they can distinguish objects that are between these two sizes, so very, very small. Not the smallest, of course, but quite small. And here we go. Here's an image that compares the two. So you've got an optical telescope, optical microscope on this side. You've got the light coming through. You've got lenses, and it focuses the light, and you can see the object which is back over here. And it makes it bigger.
Pretty much the same thing.
It is pretty much the same thing, except we have an electromagnetic lens instead of an optical lens. Almost identical operation.
Yeah, same shape and everything.
Same shape and everything. Yeah, that's right. And of course, you put your eye there with an optical telescope. You don't put your eye there with a because you get blind. Yeah. You actually, what happens is the electrons go in and they hit a fluorescent screen. Now, where have we seen fluorescent screens before? Thinking back to practical number 2, yes. That was a fluorescent screen. The electrons were hitting it, and what was it doing? It was lighting up. It was glowing. It was getting lit, yes. What happens here in the old ones, the new ones have computer sensors here, so they can put the images directly onto the computer. Happened on the older versions of these is, yeah, the electrons would go in, they'd hit the fluorescent screen, and they'd glow a certain colour. What is the problem with that? Can you have multicolour fluorescent screens? No, you probably can't. You might be able to, I don't know. I don't think you can. So there are multiple problems with that, but they of course keep working on these things. So from the previous diagram, we can see that the two types of microscopes are very similar. The difference is the swapping the light for the electron gun, and the electron gun has an operating voltage of 50 kilovolts to 100 kilovolts. Is that a lot? Yeah, it's a fair bit. That means you've got 50 kilo electron volts to 100 kilo electron volts. That's a fair bit. And that the emerging electrons have a de Broglie wavelength of 10 to the negative 12 meters. And that's that. Okay, at that point we are done, dusted, and that is the last topic before the next test. I am going to